The alkaline earth metals are generally softer than most other metals, and they react readily with water, particularly when heated. Each has two valence electrons in its outermost electron shell. They are powerful reducing agents that readily give up electrons to other substances. The element beryllium can absorb large amounts of heat, which makes it useful for spacecraft and aircraft construction. Magnesium is a light metal. It is combined with other metals to make racing bicycles, airplanes, missiles, and other products that need to be lightweight and strong. Calcium is an essential element for countless living organisms. It forms the foundation for everything from shells to teeth and bones. Strontium goes into colorful flares and fireworks, and phosphorescent paints. A radioactive version of this element is one of the most deadly byproducts of nuclear fallout. Barium is a heavy silver metal that is used in spark plugs, vacuum tubes, and fluorescent lamps. And radium is an intensely radioactive element that doctors once often used to destroy cancer cells. In their pure forms, the alkaline earth metals are shiny silvery gray metals. They have relatively high melting and boiling points, and they are good conductors of heat and electricity. These metals have a gray-white luster when they are freshly cut, but they tarnish quickly when exposed to air. The heavier members of the group tarnish especially quickly. Beryllium, the lightest of the alkaline earth metals, is hard enough to scratch glass. But barium, the heaviest, is only slightly harder than lead. The alkaline earth metals react readily with water, especially when they are heated. They combine easily with other elements, and as a result, are never found in their pure, uncombined forms in nature. Although they are harder, stronger, and denser than the alkali metals, they are nearly as chemically reactive. The alkaline earth metals are so reactive because they are very electropositive. This means that, like the alkali metals, they easily lose electrons to other elements. Let's take a closer look at the periodic table. On the periodic table, the elements are listed in order of their atomic number. The atomic number represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is surrounded by an equal number of electrons. And as the atomic number increases, generally so does the size and mass of the atoms. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. For example, there are 4 electron shells in an atom of calcium, so it lies in period 4. Meanwhile, an atom of barium in period 6 has 6 electron shells. As you read across the table from left to right, the vertical lines of elements are called groups. Elements in a group have the same number of electrons in their outermost electron shells. These outermost electrons are called valence electrons, and they dictate how elements interact. Elements in the same group generally interact with other elements in similar ways. None of the elements greater than atomic number 83 are completely stable. All of these elements, including radium, are radioactive. All alkaline earth metals reside in group 2 because they each have 2 electrons in their outermost electron shell. Because atoms need 8 electrons in their valence shell to be stable, the 2 valence electrons in the alkaline earth metals makes them unstable. Nearly as unstable as the alkali metals, which only have 1 valence electron. As a result, the alkaline earth metals easily lose their 2 electrons during chemical reactions. And as you move from beryllium to radium, the atoms' hold on their valence electron becomes weaker, making each alkaline earth metal more reactive than the one before it.
Element number 4 on the periodic table is beryllium. The atomic symbol for beryllium is Be. Beryllium is a hard, strong gray metal that can be polished to a high sheen. Beryllium gets its name from berylos, the Greek word for the mineral beryl. Beryllium is classified as an alkaline earth metal. It lies in the periodic table's second row, period 2. Each atom of beryllium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of beryllium, its nucleus has 4 positively charged protons plus 5 uncharged neutrons. Beryllium has 4 negatively charged electrons to balance its 4 protons. These electrons are found in 2 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, helium. Helium has 2 electrons distributed in a single orbital shell. The 2 additional electrons in beryllium are found in the spherical 2s orbital shell. Beryllium reacts easily and will typically lose these 2 valence electrons when combining with other elements. Beryllium is a reasonably light metal with a density of 1.8 grams per cubic centimeter. In this experiment, beryllium is placed on a scale, with a smaller piece of tungsten placed on the left-hand side. Tungsten is one of the heaviest of all metals with a density of 19.3 grams per cubic centimeter. As a result, a much larger amount of beryllium is needed to balance the smaller amount of tungsten. Because beryllium can absorb large amounts of heat, it is useful for making spacecraft, missiles, and other aircraft. It is also used in lightweight metal alloys and X-ray tube windows.
Element number 12 on the periodic table is magnesium. The atomic symbol for magnesium is Mg. Magnesium is a bright grayish-white metal with a low density. Magnesium gets its name from the ancient Greek region known as Magnesia, where magnesium ores were commonly found. Magnesium is classified as an alkaline earth metal. It lies in the periodic table's third row, period 3. Each atom of magnesium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of magnesium, its nucleus has 12 positively charged protons, plus 12 uncharged neutrons. Magnesium has 12 negatively charged electrons to balance its 12 protons. These electrons are found in 3 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, neon. Neon has 10 electrons distributed within 2 orbital shells. The 2 additional electrons in magnesium are found in the spherical 3s orbital shell. Magnesium reacts easily and will typically lose its 2 valence electrons when interacting with other elements. In this experiment, a piece of coiled magnesium ribbon is ignited in a propane flame. Reacting with the oxygen in the air, it glows and gives off a lot of heat. It is important during this experiment that the experimenters do not look directly at the bright light for too long, as it is bright enough to burn the retinas in the eye. The white residue that remains on the coil after the flame is removed is magnesium oxide. Due to the bright white light it produces when it is burned, magnesium is often used in pyrotechnics, photographic bulbs, and flares. Magnesium metal alloys are used to make airplanes, rockets, cameras, and horseshoes.
Element number 20 on the periodic table is calcium. The atomic symbol for calcium is Ca. Calcium is a soft silvery white metal that tarnishes quickly when exposed to air. Calcium never occurs freely in nature, because it is highly reactive and easily forms compounds with oxygen and water. Calcium gets its name from the Latin word calx, which means lime, because limestone is one of the sources of the element. Calcium is classified as an alkaline earth metal and lies in the periodic table's fourth row, period 4. Each atom of calcium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of calcium, its nucleus has 20 positively charged protons, plus 20 uncharged neutrons. Calcium has 20 negatively charged electrons to balance its 20 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Calcium has 2 more electrons than argon. The 2 electrons are found in the sphere-shaped 4s orbital shell. These 2 valence electrons make calcium very chemically active, and it forms compounds with many other elements. Calcium is a silvery white, hard metal, which is difficult to cut. When exposed to air, it readily forms a thin white layer of oxide called lime, so the metal remains silvery for only a few minutes. Once several pieces have been cut, they are dropped into a bowl of water. The calcium metal reacts slowly with the water, forming milky white calcium hydroxide and bubbles of hydrogen gas. After 10 minutes, the water in the bowl becomes cloudy and highly alkaline with dissolved lime. Due to its high reactivity, metallic calcium has very few uses. Its compounds, on the other hand, have many uses. Calcium carbonate is used to make white paint, cleansing powder, toothpaste, and stomach antacids. And other compounds are used to make dry wall, plaster, and natural fertilizers. The human skeleton is incredibly strong, yet remarkably light. The 206 bones that make up our skeleton support our bodies, allow us to move around the world, and protect the vital organs inside us. And every one of our bones depends on the element calcium. We use calcium to help regulate our heartbeats and clot our blood, but 90% of the calcium in our bodies is in our bones. Our bodies use calcium, mostly in the form of phosphate and carbonate salts, to form and maintain our bones and teeth. Calcium is especially important when you are young because it helps bones grow stronger, bigger, and healthier. Bones make up only 18% of our total body weight, but they have to deal with all the impacts, strains, and stresses we put our bodies through every day. Our bones are a hard mix of calcium and other minerals on the outside, but they are spongy on the inside. And the ends of our bones have a honeycomb structure of arches and struts. These formations direct the force of impacts into the stronger middle section of the bone. Being thick and hard in some places and spongy and hollow in others helps make our bones very strong, but still light. Bones are living things. They are made up of living cells embedded in the calcium carbonate matrix that makes up the hard part of our bones. These cells are constantly repairing and replacing the calcium and other minerals in bone. This becomes especially important after an injury. When a bone breaks, the body immediately sends in the repair team. Cells called osteoblasts begin their repair work by excreting a layer of liquid bone. Over time, calcium and other minerals are drawn to the damaged area, strengthening, hardening, and eventually forming a new bone. The cells are constantly on the lookout for bones that have weakened from daily activity. Here, bone-destroying cells called osteoclasts break down weakened bones so they can be built up again. Within 10 years, these cells break down and replace every bone in your body, which is a very good thing, especially for people who enjoy an active lifestyle, and the knocks that come with it.
Element number 38 on the periodic table is strontium. The atomic symbol for strontium is Sr. Strontium is a soft silver-yellow metal that can be found in 3 different crystalline forms. Strontium is named for Strontian, Scotland, a town near the mines where the first strontium-bearing minerals were found. Strontium is an alkaline earth metal and lies in the periodic table's 5th row, period 5. Each atom of strontium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of strontium, its nucleus has 38 positively charged protons, plus 50 uncharged neutrons. Strontium has 38 negatively charged electrons to balance its 38 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed among 4 orbital shells. The 2 additional electrons in strontium are found in the sphere-shaped 5s orbital shell. These 2 outermost valence electrons determine how strontium reacts with other elements. The silvery white metal strontium reacts easily with air, so this sample is protected by a thin layer of paraffin wax and kerosene. When the protective layer is burned off, the flame ignites the metal, which burns in air with an intense crimson light. When the metal burns, it produces a mixture of white strontium oxide and strontium nitride. Volatile strontium salts, such as these, are often used in fireworks and signal flares because they produce a brilliant crimson color. Most strontium is used to produce glass for television picture tubes. The element is sometimes combined with iron to make magnets and is also used in making pyrotechnics and phosphorescent paints. In the spring of 1986, the worst nuclear reactor disaster in history occurred at the Chernobyl nuclear power station in northern Ukraine. To run a test, engineers had deliberately disabled the emergency backup systems in one of the reactors. But instead of simply testing the reactor, they accidentally started an unstoppable nuclear chain reaction in the core of reactor number 4. On April 26th, the reactor exploded, ripping the top off the reactor containment building and blowing radioactive material high into the atmosphere. As the reactor core burned, fires spread to the nearby buildings, and as they burned, the core released more and more radioactive materials. But as the danger of the explosion became more apparent, they called for the evacuation of Chernobyl, Pripyat, and other nearby towns. The fires at the Chernobyl plant raged for more than a week, and the burning nuclear core was brought under control only after a cement mixture was dropped onto it from the air. The explosion and the fires released 8 tons of nuclear fallout into the atmosphere. Nuclear fallout is made of radioactive particles that are scattered through the Earth's atmosphere by winds and air currents. The Chernobyl release created a huge cloud of fallout that caused extensive harm across Eastern and Northern Europe. The serious danger of nuclear fallout is that it contains radioactive isotopes of the elements strontium, cesium, carbon, and iodine. In high doses, these isotopes can cause severe health problems or even death. One of these isotopes, strontium-90, remains radioactive for decades. And since strontium and calcium are both chemically similar alkaline earth metals, the tissues of animals and plants absorb strontium as if it were calcium. When humans consume contaminated foods and liquids, the strontium-90 accumulates in their systems and can cause genetic damage or lead to leukemia, bone cancer, and other diseases. Strontium is particularly dangerous for children because it is easily deposited in their growing bones. Ukrainian officials have estimated that at least 8,000 people died as a result of the Chernobyl accident and the cleanup of the radioactive materials it released. Millions of Europeans live on radiation-contaminated land, and countless more will likely suffer harmful long-term effects from the Chernobyl release of strontium and other radioactive elements. Element number 56 on the periodic table is barium. The atomic symbol for barium is Ba. A soft, heavy, silvery gray metal, barium oxidizes very rapidly. Barium derives its name from baris, Greek for heavy. Classified as an alkaline earth metal, barium lies in the periodic table's 6th row, period 6. Each atom of barium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of barium, its nucleus has 56 positively charged protons, plus 82 uncharged neutrons. Barium has 56 negatively charged electrons to balance its 56 protons. These electrons are found in 6 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, xenon. Xenon has 54 electrons distributed among 5 orbital shells. Barium has 2 more electrons than xenon. These 2 valence electrons are found in the spherical 6s orbital shell and influence how barium interacts with other elements. Barium is a metallic element resembling calcium chemically. Here, a piece of barium is placed in a very hot flame. It burns with a very bright blue-green flame and melts easily. Although barium ores are heavy, metallic barium is in fact quite light, with a density approximately half that of iron. Barium nitrate burns with a bright green color and is used in fireworks and signal flares. Barium is used in vacuum tubes as a getter, a material that combines with and removes trace gases. Barium sulfate is a good absorber of X-rays and when swallowed can be used to produce X-ray images of the intestinal tract. Barium peroxide forms hydrogen peroxide when it is mixed with water, and it is used as a bleaching agent that activates when wet.
Element number 88 on the periodic table is radium. The atomic symbol for radium is Ra. Seen here in the glowing dials of this watch face, radium is a brilliant white metal that blackens when exposed to air. Radium glows in the dark and is extremely radioactive, more than 1,000,000 times more radioactive than uranium. Radium gets its name from the Latin word for ray, radius, because of the radioactive rays it emits. Radium is classified as an alkaline earth metal. It lies in the periodic table's 7th row, period 7. Each atom of radium consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of radium, its nucleus has 88 positively charged protons, plus 138 uncharged neutrons. Radium has 88 negatively charged electrons to balance its 88 protons. These electrons are found in 7 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, radon. Radon has 86 electrons distributed among 6 orbital shells. Radium has 2 more electrons than radon. Both of these electrons are found in the sphere-shaped 7s orbital shell. It is these 2 valence electrons that determine how radium reacts with other chemicals. Radium is represented here by the display of nuclear fireworks inside an instrument called a spinthariscope. A small piece of radium is sealed within the device, and as the radium atoms undergo natural radioactive decay, they release alpha particles. These alpha particles travel at over 20,000 miles per hour and, when they strike a zinc sulfide screen inside the device, photons of visible light are released in a process called scintillation. This produces the thousands of tiny flashes of greenish light that are visible through the device's magnifying lens. Each flash of light indicates a single atom of radium decaying. Radium is highly radioactive, so its use is limited. In the past, small amounts of radium were used to make glow-in-the-dark paint for watches, aircraft dials, and other instrument displays. But less dangerous alternates have largely replaced those early uses. Today, the element is primarily used in the treatment of cancer. The gamma rays it produces kill cancer cells, and radium is used to produce radon gas that is also used to combat some cancers. One of the most significant medical advancements of the 20th century was the invention of nuclear medicine. Nuclear medicine allows doctors to use small amounts of radioactive elements to get an inside view of the patient's body without surgery. When doctors find tumors, radioactive materials may also be placed directly into a patient's body, where the radioactivity helps fight the growth of cancer cells. The roots of nuclear medicine began in France in 1896 when Professor Henri Becquerel discovered that uranium was radioactive. Becquerel's discovery of radiation soon prompted other scientists to search for radioactive elements. Two scientists, the Polish-born Marie and Pierre Curie, made discoveries that would change the face of medicine. Using equipment designed by Pierre, Marie Curie measured and analyzed thousands of mineral samples. In early 1898, she discovered a second radioactive element, thorium. By the end of that year, the Curies had discovered two more radioactive elements, polonium and radium. Thorium and uranium had about the same radioactive strength, but polonium's was 10,000 times greater. And radium's strength was more than 1,000,000 times that of uranium's. The discovery of such a highly radioactive element rocked the scientific world.
Their work was extremely important. The discovery of radium opened up a whole new era. It's been described as the nuclear age. Pierre and Marie were the start of modern physics.
Doctors soon discovered that exposure to strong radioactivity, like that given off by radium, could kill cancer cells. An early medical technique involved inserting radium needles directly into tumors. Radiation treatments helped millions of cancer patients throughout the world battle their disease. Although iridium, iodine, and cesium have replaced radium in radiation treatment, nuclear medicine remains an effective method for detecting and treating cancer.
Radiation therapy is a localized treatment of cancer involving external beam radiation and insertion of radioactive materials into the tumor. Radiation therapy was actually in use within a year of the discovery of radiation. Since then, it had become a highly sophisticated treatment of cancer. Of all cancers, radiation is the second most used after surgery.
At the time of the Curie's discovery, scientists were unaware of the harmful effects of prolonged exposure to radioactivity. While radioactive elements can kill cancer cells, extended exposure to them can also cause cancer, anemia, and other disorders. Marie Curie's work with radium produced painful scars on her hands. And worse, her repeated contact with radioactive elements eventually brought her life to an end. She died of leukemia before reaching the age of 70. But her pioneering work made her the first person to win 2 Nobel Prizes, laid the groundwork for countless medical advances, and prolonged the lives of millions of people.